Good. Here to give you guys an example on how to deal with linearizing nonlinear equations. So basically in this particular setup we've got some inverted pendulum where he's gliding along. We've got this inverted pendulum sitting along some form of rolling device where we're going to apply some force Fc to shift it to and fro to try to stabilize it and get this theta back up to 90 degrees. So we see in this diagram we've got the center of mass here at a distance of L away from the body. Is rotating some amount theta. We're trying to get that back up to stable, and we're keeping track of how much force do we need and what kind of x do we need to be able to do this. And so basically they give us these two equations of motion which govern how this thing is going to work, and then they say, all right, well, we've got these nonlinear equations, but we want to express them in terms of some linear equations, just how we can make our lives easier in terms of plotting and everything else like that, even for solving purposes. And so the way that you want to do this is using the small approximation technique, and we're going to assume that x dot, x double dot, theta, theta dot, and theta double dot are really small. So using this technique to linearize these nonlinear equations, basic thought process behind this is wherever you see some term, whether it's an x or a theta, and it's squared, like that, or like times, let's say it's a theta times a theta dot, or a theta times a theta double dot, something like that, that squared term is going to go to 0. If we see a sine of x, we can just rewrite that as x, or sine of theta would be theta, and a cosine of blank would just be 1. So using that and looking at the first equation, how can we rewrite this? So we see the mass of A plus the mass of B multiplied by x double dot. So x double dot is just going to remain as x double dot. So we write that again, mass of B times L times cosine of theta. As we said before, cosine of something is just 1. So this guy is going to go to 1, and then this theta double dot is going to remain. So we've got the mass of B times L times 1 times theta double dot, and then we see in MB, L, sine of theta. We know the sine of theta becomes a theta, and then we're multiplying it by a theta dot squared, and as I said before, if we've got the square term, this guy is going to go to 0. So we've got this MBL theta multiplied by 0. So then this whole term obviously is just going to go to 0. And all that is equal to this forcing function that we're this force that we're trying to stabilize it with, or stabilize the pendulum with. So then looking at the second equation, how do we write this one? Same logic. So MBL cosine of theta becomes a 1, x double dot remains, IZ, it's just a constant, so he remains, MB, L is just, L is a constant, it's not a variable, so it's not one of these that's changing, so he's going to remain. Theta dot is just rewritten, and then once again the mass of B, GL, sine of theta becomes a theta, and then equal to 0. So after linearizing these equations, then the next question becomes, well, how would I write this in terms of a matrix form, just to make my life easier for computation? And so what you want to do is, typically it would be an x double dot, a theta double dot, and then it'd be an x dot, a theta dot, and then the x and a theta. But we realize when looking at these equations, like, we don't have any x dot or theta dot terms, so I just took them out. But if we're to try to rewrite this expression, this top line being equation 1 and the bottom line being equation 2, how do we write this? So we'd see, all right, well, in the first equation, do I have any x double dot terms? So I scan through here and I'm like, all right, well, I've got